Okay, this is my second attempt recording this video. I had a typo in one of the last problems that really threw me for a loop and I couldn't fix it on air, so we're trying again. So today we're going to go back and think about this idea of rates of change and derivatives. And we've talked about this in class already, but this is so important that I want us to spend a whole nother class period emphasizing the fact that derivatives give us slopes of tangent lines, they give us instantaneous velocity, they give us instantaneous rates of change. And let's go back and once again think about why that's the case. And like I said, we've talked about this before. So if you're like, well, Dr. Greger, I already know how to do this, that is awesome. But I want to make for sure and for certain that all of us are really happy with this and why this connection is true. So let's think about a penguin population on a little island. And so we have maybe some function that gives us the population of penguins. So we'll make this P. This is the number of penguins. Penguins are probably my favorite animal. And this is T, which is maybe measured in years since 2000. And so our penguin population, maybe we start out with a few penguins, it grows quickly. And then because the island has limited resources, it's going to kind of settle out at some carrying capacity. So this is our penguins on the island. And so let's look at that expression P of X minus P of A over X minus A. This thing is called a difference quotient. This is what we have been seeing inside of our limits for finding derivatives. And let's once again think about what that tells us. So we have X, we have A. So this point up here is P of X. This is P of A. So looking at P of X minus P of A, that's a change in Y values, over X minus A, that's a change in X values. That is giving us the slope of a secant line. And remember that this is going to, instead of just being the slope of a secant line, in terms of our penguins, what is this telling us? This is telling us the change in the number of penguins over the change in time. So that is giving us an average rate of change of the penguin population. So this would be telling us maybe I get like 10 out from this, 10 penguins per year. On whatever time increment I was looking at, that would tell us that the population was increasing at 10 penguins per year on average. So this is an average rate of change. But what if I want the instantaneous rate of change? What if at 5 years, I want to know how quickly is the penguin population changing right now? That's where we need our limit. That's where we're looking for the slopes of tangent lines. And so that's where we stick a limit in here, and this is going to give us an instantaneous rate of change. We remember in order to think about our units, we look at what the units on these two pieces are. So this is the number of penguins, and then this is the time, the years. So this case, the instantaneous rate of change would be measured in penguins per year. So if we were looking at like P prime of 6 and we got 10 out, then this would be saying at 6 years, which would be 2006 in this case, the population of penguins at that particular instant in time is changing at 10 penguins per year. We could estimate then that in 2007, there will be 10 more penguins than there were at the beginning of 2006. Okay, so that is what derivatives are telling us. So for this first example, we're going to do just a velocity example. So this one gives us a particle that's moving in a straight line. We're given the position function of this particle. And the first part just asks for an average velocity. So an average velocity is just going to be a change in position over change in time. No limits, no derivatives here, no calculus actually. So if I plug 4 into this function, I get 2 out. If I plug 3 in, I get 3 out actually. We have 4 minus 3, so this is -1 over 1, which is -1. The units here, position is being measured in meters, so we have meters up here, and time is measured in seconds, so this will be meters per second. Okay, so that is the average velocity. So on average, between the 3 and 4 seconds, the particle was moving backwards, that's what the negative means, at 1 meter per second. Now, if I want the instantaneous velocity, that's asking what would our speedometer read at that particular instant in time? That's asking for a derivative. So this is asking for s prime of 4. And so we can just go about computing this like we have done before. So this is a limit as t approaches 4, s of t minus s of 4 over t minus 4. So if we plug in our function here, we have t squared minus 8t plus 18 minus s of 4 we said was 2 over t minus 4. So if we combine that 18 and the 2 up here, we're going to have a 16 t squared minus 8t plus 16 over t minus 4. Now we can factor. So we're going to get t minus 4 times t minus 4 over t minus 4. Those cancel out. When we plug 4 in, we get 0. The units here are still meters per second because up here we still have meters in seconds. So what this means, if this particle looked at its speedometer would be say it was not moving at all. And so this particle is at rest at that second. It might not be at rest for very long, but it has briefly paused at 0 seconds. Okay, so we have one more example here. So this example is going to look a little different in computing the derivative. So we have a table that gives us information about the debt in the US, how much money the US owes. This gives us approximate values, and we want to interpret and estimate the derivative at 1990. So let's just start by drawing what this looks like vaguely. We're not going to be very precise here. So we have 1980, 1985, 1990, 1995. I'm going to stop here because we don't need all this information. So it started out at 930, then it was at 1945. Once again, not being super precise here, then we have 3233, and then we have 4974, something like this. Okay, so we could maybe connect the dots. We see that the debt is increasing here. So we're trying to estimate the derivative at 1990. So that is the slope of this tangent line. So that value is going to tell us how quickly the debt is changing at this particular point in time. The units are going to be the change in, well, we're going to look at change in debt over change in time. The units on the debt are billions of dollars, and the units on time are years. So this will be measured in billions of dollars per year. So the value that we get for this derivative is going to tell us how quickly the debt was changing in the year 1990. Okay, and now we need to estimate this. We don't have a function to work with. So the way that we're going to estimate this is with slopes of secant lines. So maybe let's look at the secant line between these 2 points and the secant line between these 2 points. Just pick the points closest to the one that we care about. And then let's average the green and the blue values to try and get the red line there. So for that blue line, so this will be an average here. So that's looking between these 2 years. So the slope of that line will be the 3233.3 minus 1945.9 over 1990 minus 1985. When you do that calculation, you get 257.48. And then that green line there, that will be the 4974. Notice I had a typo on this sheet and I fixed it here, so you should fix that before you go too far. Looking at these two values minus the 3233.3 over 1995 minus 1990. You end up getting 348.14 out from that. So each of these on their own could estimate the slope of the tangent line. We could average these as well. So just add them together and divide by 2 to get maybe a better estimate. Sometimes this is a good idea, looking at 2 secant lines and then finding the average of them. If I did my math correctly here, if I typed into my calculator correctly, you get approximately 303. This is in billions of dollars per year. Okay. And so that tells us that at 1990, the national debt was increasing at a rate of $303 billion per year, which is a lot.